This session is about defining pore water pressure conditions in slope W. Once again, here is our key list of components, and certainly one of the very important aspects of any stability analysis is to define the pore water pressure conditions if we want to use effective strength parameters. Once again, we have an entire chapter on defining pore pressures in the Slope W engineering book. The main issues in any stability analysis is defining the pore water pressures. If there were no pore water pressures, we would not have stability problems. So almost all stability problems, slope stability problems in particular, arise because of some pore pressure conditions or adverse pore pressure conditions which naturally affect the shear strength of the soil. So a proper definition of the pore pressure regime is an essential component of any stability analysis. This is particularly true if we are going to do an effective stress analysis, and in this session on defining trial slip surfaces, we pointed out that the position of the critical mode of failure is controlled by the definition of the strength parameters that are used. And we pointed out in that session that the most realistic position of the critical slip surface is determined when we use effective strength parameters C prime, phi prime together with a realistic pore pressure distribution. So if we want to determine a realistic picture of the critical mode of failure, we should be using effective strength parameters, which includes also that we must have a realistic picture of the pore water pressure conditions. As with all aspects of slope W, there are many different ways of defining pore water pressure conditions in slope W. The most common perhaps is to define a piezometric line or piezometric lines. There are other more historic means such as an R sub U parameter or a B bar coefficient. An R sub U parameter expresses the pore pressure as a portion of the slice weight. Perhaps half of the slice weight it goes into pore pressure or is a measure of the actual pore pressure, or a quarter. I'm not going to spend a lot of time here on talking about R sub U parameters, but I will spend a little bit of time on the use of B bar, which is useful for simulating construction-induced pore pressures. If you do not have a finite element analysis describing the pore pressure conditions, then a spatial distribution defining discrete points can be quite useful. Spatial distribution using discrete points is useful for irregular pore pressure conditions such as may occur under Artesian conditions, for example. And then, of course, one of the real powers of GeoStudio is that pore water pressures coming from Seep W or Sigma W or Quake W can be used in a slope W stability analysis. A very common way of describing pore water pressure conditions in slope W is through the use of a piezometric line. All too often, only one piezometric line is used to describe the pore water pressure conditions. And this is done often, I'm certain, because people think of the water table and think of the piezometric line as the water table within the slope configuration. There are several features about the piezometric line that are worth highlighting and mentioning. Number one is that each soil type can have its own piezometric line. This means that there can be many different piezometric lines. For example, if you had 3 different soil types, each soil type could have its own piezometric line. This is not done often, but the feature is there for special cases. The second thing to note is that when you use a piezometric line, the pore pressure that is computed at the base of a slice is simply determined from this vertical distance. The pore pressure is equal to the height of the water times the unit weight of the water. In a two-dimensional flow system, this is not entirely correct. And if you remember from flow nets in your university studies, that when we have a flow where the flow is not entirely horizontal, there may be some equipotential lines like this, and the equipotential lines are perpendicular to the piezometric line. And so in actual fact, the pore water pressure here is only this much. And in this sense, using piezometric lines in slope W is an approximation. But in light of everything else that is known about the soil conditions, it is not a bad approximation and used very extensively in many, many different situations. But it is worth recognizing that to some degree, particularly if there is flow that is, there is a significant amount of vertical flow, then the equipotential lines are such that the pore pressure at the base of the slice is not exactly represented by the height, the vertical height from the base of the slice up to the piezometric line. Now let's look at the use of B-bar to simulate some construction pore water pressures. Let us assume that we have an sand embankment here. And this sand embankment was placed on this clay foundation, and that the water table was at the surface of the clay before the sand was placed. The sand is so pervious that it will have no excess pore pressures, and therefore there will be no pore pressures in the sand. At the base of slice 12, for example, we can spot check what the pore pressure should be, and prior to the sand being placed, the pore pressure would have been gamma H water is equal to 10 times 1.26 is equal to 12.6 kPa. The excess pore pressure produced by placing the fill would be equal to the height of the sand, HS, times the unit weight of the soil, gamma sand, times B bar, is equal to 8.61 times 18 times 1.0 for this particular case, results in a pore pressure of approximately 155 kPa. So the pore pressure that will be used at the base of the slice 12 in slope W will be 155 plus 12.6 is equal to 167.6 kPa. Let us now open up SLP 17. Make sure that you start out in define view. We need to look at key in pore pressures. We have defined one piezometric line, and under the Materials tab we see that the piezometric line does not apply to the fill. Notice that the piezometric line does not apply to the fill. The piezometric line, however, does apply to the foundation. So piezometric lines can be identified with certain material types. Secondly, we need to look at define B bar. And here, notice that the fill weight adds to the pore pressure. The foundation weight does not add to the pore pressure. There is no excess pore pressure, or no pore pressure is developed in the fill due to its self-weight. Therefore, B bar is 0. The foundation, however, does respond to the fill weight, and the B bar in the foundation is 1. So repeating then, the foundation has the B bar of 1, but the self-weight of the foundation clay does not add to excess pore pressure. The fill has no excess pore pressure, but the weight of the fill adds to the excess pore pressure in the clay. Let's go to the results view and say draw a graph and look at a pore pressure distribution versus slice number. Notice that if I hover over these data points, I see the x-coordinate and the y-coordinate. So slice 10, slice 11, slice 12. And exactly as we computed by hand, the pore pressure at the base of slice 12 is 167.58 kilopascals. So this shows how a B-bar can be used to simulate excess pore pressures that might arise from the placement of an embankment, for example. As I mentioned in the introduction to this pore water pressure session, when we have irregular pore pressure distributions, such like might arise from artesian conditions, or sometimes if data is in the form of pore pressure contours, we can use data points to describe the pore pressure conditions. In essence, what is required is that at a series of XY locations, we can specify the pressure head. The pressure head H is equal to the pore pressure divided by the unit weight of the water. So we can think about a piezometer being at this location and the water arising a certain distance. This would be the pressure head H. So you can imagine at a series of points what is the pressure head at these XY locations, and then slope W can either use a linear interpolation or a Kriging interpolation to develop pore pressure contours. Later on, these contours, or the results of the Kriging, are used to determine the pore pressures at the base of all of the slices. We can illustrate this a little bit further by opening up SLP 18. SLP 18 has one analysis in it, and the analysis here is to illustrate how pore pressures can be defined by defining the pressure head at a series of XY locations. Once again, it's useful to click on the All Objects Zoom button. And it's probably best to illustrate how this works by saying key in, spatial functions, pressure head. In this case, we have one pressure head function. There could be several pressure head functions for different materials, but usually one pressure head function is adequate. And to those of you who were part of the shear strength session where we showed how shear strength could be defined by a spatial function, this function here and this key in box works exactly like it did for shear strength. We can click on any point and we see that the corresponding point is highlighted in this edit box. So it is a matter of specifying a series of XY coordinates and specifying the pressure head at that particular location. For example, if the pressure head here was 22 instead of 20 and we tab out, then we see that the contours change in response to this pressure head at that particular location. I'm going to click the undo button here and click back on the function to go back to where I was. So I won't spend a great deal more time on this here because it is so similar to what we did when we looked at undrained shear strength distribution on a spatial basis. The data could be imported from another spreadsheet, for example, or it can be the data can be entered directly in these edit boxes here. But it is also possible to draw the points, and for example, if you had a contour map and some ideas of the contours, you could just provide a series of data points along each contour. Once again, it's possible to do a linear interpolation or a Krieg surface or none. In this case, we have used a Krieg surface. If we now look at the results view, once again we can say draw a graph, add a graph, look at the pore water pressure distribution, slice data, pore water pressure versus slice number, and this is the pore water pressure distribution that would result from the contours. It is possible to pick any particular slice, for example, slice number 14, and we could then go back into the cross section to spot check that the pore pressure at the base of slice 17 or 14 is approximately 750 kPa. I will leave that up to you to do. I won't spend any more time then on spatial distribution of pore water pressures. This is a very useful technique as I've already said, if you have irregular pore water pressure distributions, particularly for things like upward flow arising from artesian conditions. And I would say this method is useful somewhere between defining a piezometric line and using the results from a SEEP-W analysis. Obviously, in our view, if you have SEEP-W, then it would be best to establish the pore pressure conditions using a SEEP-W analysis, and then to use the SEEP-W pore water pressures in the slope-W analysis. There is one key point that I'd like to point out about using the finite element results in slope-W. And that is that The pore water pressure at the base of this slice is not this distance. We do not use the blue line in slope W. In other words, stated in a different way, we do not import the blue line into slope W and use that to describe the pore water pressure conditions. What slope W does, it takes and it says, here is the base of the slice, and which element is the base of the slice in. And once the element has been defined, or found rather, that encompasses the base of the slice, then from the finite element analysis we know the pore water pressure or the total head at each node, corner of the, or node of the element. And say the base of the slice is here. The procedure then is to say that the pore water pressure, or better say the total head is, well, let's do it this way. The pressure head is equal to the total head minus the elevation, and the pressure head at the particular point in the element is the matrix of interpolating functions times the heads at the nodes. By doing this, we use the pore water pressure at the base of the slice exactly as it was determined from the finite element analysis. It would be an approximation to import the piezometric line or the zero pressure contour line into slope, because if we did that, we would be using this vertical distance. That's not what we want to do. We want to use the equipotential lines and use the correct pore water pressure, and we can do that by using this equation here to get the pore pressure at the base of the slice. You don't need to remember this equation. What you need to remember though is the fact that, as I have said several times already, is that the blue line or the zero pressure contour line is not imported into slope when you use finite element results. We use the actual pore water pressures in each one of the elements to determine the pore pressures at the base of the slices. Let us go to GeoStudio now and open up SLP09. File, open. SLP19. We can turn off the snap to grid. Now the first thing we need to do is look at the analysis tree, and we see that we have started here by doing a steady state seepage analysis. So the first thing that was done was to do the steady state seepage analysis using seep W. Then going back to the define view, we look at the downstream stability first, and under the analysis tree we say, where am I getting my pore pressures from? The pore pressures are coming from my parent analysis. Who is my parent? The parent is the steady state seepage analysis. So here we identify who is the parent. So in this particular case, we are obtaining our pore pressures from the parent, and the parent is the steady state analysis. This is how slope W knows where to go to find the pore water pressures at the base of the slice. We can now go to the results view, and once again say draw a graph of pore water pressure. Let's add a new graph here called pore water pressure and pore pressure from slice number, and you see here now that we have some negative pore pressure and some positive pore pressure. I won't talk about the other aspects of this particular problem. The idea here is to illustrate how pore pressures are taken from SeepW and used in a SlopeW analysis. We can do the same for the upstream case. And what is important here now is that two things have happened. We have determined the pore pressure at the base of each slice from the finite element analysis, but we have also determined the water weight here. From the SeepW analysis, SlopeW took a look at what is the pressure here at the top of the slice, and it determined that the pressure here is positive, and consequently SlopeW says, oh, in that case there must be some water weight on the slice. So even when the pore water pressures come from a SeepW analysis, the weight of the water that is impounded on the slope automatically gets included in the analysis. The previous example that we looked at was a fairly simple case of a homogeneous dam with a reservoir on one side. The pore pressures were not all that irregular, but here's an example where the pore pressure is quite irregular. In fact, we have a perched water table. So this is a perched water table here, and you notice a flow line. Infiltration is in an unsaturated zone, then it goes through a saturated zone, then it is in an unsaturated zone, and then it goes back in a saturated zone. In other words, the pore pressure is negative, then it's positive, then it's negative, then it is positive. In a case like this, it is impossible to describe the pore water pressure conditions with a piezometric line, and this is where the use of SeepW computed pore pressures in slope really begins to shine. Let's look at this a little bit more detail by opening up SLP 20. SLP 20 Looking at the analysis tree, once again you can see that we first did a SeepW analysis, then we did a slope stability analysis. Once again, the pore water pressures, they come from the parent, and the parent is the SeepW analysis. Taking a look at the results first of the seepage analysis, what we have done here is we have simulated the infiltration of rainfall. And if the rainfall is a particular rate, then it will produce a perched water table. When there is a layer here, there's a layer here that has slightly less permeability than the soil above it and below it. Once again, you notice that there is a flow line here through the unsaturated zone, then it goes through the saturated zone, unsaturated, and then saturated. The most interesting part in the context of pore water pressures now is to take a look at the SlopeW results. And once again we say draw a graph of pore water pressure, and you see here that the pore water pressure is negative at the start, then the pore water pressure goes positive where the water table is perched, then the pore pressure goes negative, and then it again becomes positive. As I have already said, a pore pressure distribution like this, it is not possible to describe it with a piezometric line, and something like a SEEP-W analysis is required for this case. It could be done with a spatial variation or a spatial function of pore pressure head specified, but in all likelihood, for you to know where the perched water table is, you would have done a SEEP-W analysis anyway, so you might as well use the SEEP-W results in SLOPE-W. This then brings us to the end on this overview of the various ways that pore water pressure conditions can be defined in a SLOPE-W analysis.